Right, now we're recording. So today's talk is by Maarten Solleveld. His title, you can see there, is Hochschild homology of finite type algebras. Please, Maarten, go ahead.
Yes. Well, thank you for the invitation to speak in this seminar. Well, so this talk is about, well, say, non-commutative algebraic geometry. And well, this is a topic in which I have been involved for a long time, at least 10 years, but I do it only part-time. Most of the time I actually work in representation theory. So this talk was a good opportunity to revisit some things which I had done not too long ago, like almost a year ago. And well, this was written down in a paper together with David Kazhdan. So yeah, it's not a very long paper, so the talk will also not be long, but I will try to approach it from a somewhat general viewpoint. So let's see. Yeah, like this. So first, how I want to get in is to look at a very, well, simple situation where you can compare, on the one hand, algebraic objects with, on the other hand, objects from differential geometry. So in particular, I'm thinking here of differential forms. And well, one interesting example is where you look at the varieties C cross, and inside there you have the circle, and you can compare differential forms on those two. And it's, well, I mean, this, of course, there's one-dimensional, so there's not so much choice. And it's easy to see that if you take the algebraic differential forms on C cross, and you tensor them up with smooth functions on the unit circle, you actually get all smooth differential forms on the unit circle. And well, since this is non-commutative geometry, we immediately tend to phrase this in terms of algebra, so then that you can then put it in non-commutative terms. So first, differential forms can be, well, constructed via algebras of functions. That's one of the standard constructions. Well, maybe this omega of a ring of functions is a bit funny notation, but I'm just using it to make my point. And well, then the next step is, of course, you say, okay, this was just one example of one variety inside which you had a particular real submanifold. And yeah, well, in that setup, it actually works quite general. If you take any affine variety defined over the real numbers, and you compare the complex points with the real points, where you say the complex points are an algebraic variety, and they have this Zariski topology and algebraic differential forms. On the real points, you have a smooth manifold, so you must assume it's not singular in some way. And then you can say you can tensor the algebraic differential forms up by tensoring with smooth functions on the real manifold, and you get all smooth differential forms. Okay, well, and the goal of this talk is to, well, to generalize this to some classes of non-commutative algebras, and the way to generalize it is by rephrase things first in terms of Hochschild homology. So, well, let me say you some things about Hochschild homology. Maybe you know it already, but then it's just a reminder. So well, okay, let me first start with one definition. There are various definitions that you can encounter, but the one I like best is as a torsion functor. So you take an algebra, and to avoid complications, I say it's an algebra over a field. And then, well, you can look at, well, this algebra considered as a bimodule over itself. And then the definition of the Hochschild homology is you take the, well, the torsion functor, the nth torsion functor considered as bimodule over itself, and then, well, you take it 2 times. And this will be, it will be some vector space over your given field. And well, if you look in literature, there's also definitions in terms of an explicit differential complex, which you can write down, and then you write down an explicit differential, and it's just the homology of this complex. But the complex is then usually chosen in such a way that this is what it computes. So, well, if you define it in this way, then some properties are rather straightforward. So that fact that this is an additive functor really follows more or less directly from this definition. And well, you also have a Kunis formula. So in the sense that if you want to compute the Hochschild homology of a tensor product of 2 algebras, then, well, if you plug in the Tor definition, you basically have to take the tensor product of 2 differential complexes and then compute the homology of that, and that will just give you the tensor product of the Hochschild homologies of these 2 graded in the appropriate way. And well, another thing which is standard property of Hochschild homology is that it is Morita invariant. So if you take an algebra and you replace it by m, so a certain square size matrices over this algebra, that's what I mean here. This is m times n matrices with coefficients in A, then the Hochschild homology doesn't change. And this is again something, if you write it out in terms of an explicit differential complex that computes the Hochschild homology, well, this is an exercise. And if you do it in terms of the definition as a Tor functor above this, Morita invariance is kind of obvious because the category of bimodules doesn't change by replacing A with n times n matrices over A. And well, further, if you take torsion functors of some modules, then usually you lose the module structure, so it's not a module over A anymore. But in fact, it turns out in such cases that it's still a module over the center of A. This is something which is actually a bit different from other homology theories. Like if you take standard cohomology of some space, it will not be a module over continuous functions on this space, something like that. So this only indicates that it's a rather fine invariant which allows still rather large outcomes. Okay, so let me discuss some basic examples. So the most basic example is just if you take the complex numbers, so the algebra functions on a point, and then you recover the same algebra in degree 0, and in positive degrees you get nothing. Well, basically is that this C is just it's a semi-simple algebra, or actually it's a simple algebra. So every module is projective, and these Tor functors, they just disappear. And while the same argument applies to other slightly larger algebra. So if you take the group algebra of a finite group, well, I take it here over the complex numbers to avoid trickiness with positive characteristic dividing the order of the group. Then this is in fact, as we know, a finite dimensional semi-simple algebra, and you can rewrite it as a direct sum of matrix algebras associated to the various irreducible representations of the group. And then you can apply the properties, well, the additivity property and the Morita invariant properties to immediately compute this. And you see that again in degree 0, you get something like the space of irreducible representations and then matrix from vector space. And in positive degrees, you get nothing. So here you see some well, simple-minded relation between Hochschild homology and irreducible representations of an algebra already. And yes, well, so this relation between Hochschild homology and representations persists to general algebras, at least for the zeroth Hochschild homology. So, well, firstly, well, it's not immediately obvious from the definition, but if you write down a complex, it's very easy to see that the Hochschild homology in degree 0 is just, you take the algebra A and you divide out all commutators, at least if it's a unit of algebra A. So that's an easy thing. And well, since any commutator has trace 0 on an irreducible representation, this in fact gives you kind of, well, if you pair it with the representation via the trace pairing, this gives you in fact a linear function on this HH0. So, well, at least if you do it with a finite dimensional representation so that the trace of the representation is well defined. So this HH0 can be paired with the, well, say the Grothendieck group of all finite dimensional representations of your algebra. And well, in good cases, this is in some sense a non-degenerate pairing, and this sometimes helps you to, well, to say something about the number of irreducible A modules, or maybe in some particular cases, it can even be used to classify representations of certain algebras. I actually used it to classify representations of particular kind of Hecke algebras. So this HH0 is in fact the most useful of these Hochschild homology functors. The higher Hochschild homology functors, they are, well, they're there. But in terms of, say, representation theory, it's not so clear what to make of it. There are other uses, but they go, well, in other directions. So one use is that if you go to a dual theory of Hochschild cohomology, then you can make sense of, well, HH2 and HH3 in terms of extensions of your algebra or of bimodules. But this is not a very strict. You have to actually to modify your functor a little bit more. So this is very loosely some application of higher Hochschild homology. Another well, application or use of it is that you can start with this and then compute other invariants of your algebra if you like. So people are sometimes interested in cyclic homology or periodic cyclic homology or K-theory in one of its versions. And well, starting from Hochschild homology of an algebra, you can at least compute the cyclic homology via, well, another differential and another homology process. And from there, you may also approach to the K-theory or rather the topological K-theory of some algebra. So, so the Hochschild homology, if you regard it in this way, it determines the cyclic homology, so it actually has more information. And then, on the other hand, if it has more information, then you can already guess it's more difficult to compute. And indeed, given an arbitrary algebra, it is usually extremely hard to compute the Hochschild homology. Well, probably degree 0 is doable usually, but higher degree is very difficult. And well, if you try to analyze how does this come, well, what is the problem? If you compare it with, say, well, standard cohomology theories, then you have notions like excision, or in topological K-theory, you have the exact hexagon, or you have, say, long exact sequences. And these would typically be used to compute invariants of algebras in terms of, well, reduce them to invariants of simpler algebras and compute those and then put it together in some exact sequence. But for this Hochschild homology, well, the standard thing which you would like to do is you take your algebra, you take an ideal, you divide it out, and you get an exact sequence, and then you hope that you get also a long exact sequence of Hochschild homology groups so that you can reduce the Hochschild homology of A to the Hochschild homology of some ideal and some quotient of A. But it turns out this doesn't work. At least, well, it does work if the ideal A itself is a unital algebra, but most of the time it's not a unital algebra, and then most of the time you do not get long exact sequences from such a sequence of algebras. So that's one cause why it's difficult to compute Hochschild homology groups. Okay, so now let me specify to the case of commutative algebras, and let's see how closely related to differential forms they are. I mean, it's of course common knowledge in commutative geometry that Hochschild homology is the version of differential forms for non-commutative algebras, but in fact the analogy is not precise even for commutative algebras. So let me start, well, with the simplest example that we didn't treat yet, say the polynomial algebra in one generator. And well, so how do you compute this? Well, let's just use the Tor definition. We plug in the Tor and we compute it. So first, the algebra over which bimodules are defined is tensor product of A with its opposite algebra. So that's just A tensor A, which is just a polynomial algebra with two generators. And to compute this Tor group, we need to make a projective resolution of this A as a bimodule, and then tensor it over this bimodule ring with the other A, and then take the homology. So first start with, okay, let's make a projective resolution of bimodules. So this is the module we want to resolve, and in this case you have it's a very short causal complex. You take the algebra with two generators. You can map it to the algebra with one generator by dividing out the difference of these two generators. That's over here, divide out this ideal. And then to make it into an exact sequence, you go from, again, this algebra to the middle term by multiplication with the difference of these two. And that's in fact the projective resolution. And then the Tor definition says, okay, you tensor this projective resolution with the module A over this A tensor A op, and you get this simple complex, and now the map actually disappears because it was X minus Y, but if you tensor in this way, then X and Y become identified. So actually the homology is just the homology of this simple complex, which is 0 in degree 0, and it's Cx in degree 0, and also Cx in degree 1, and in other degrees you have nothing. So that's very good. In this case, you don't see it as differential forms, but of course we know that Cx is in degree 0. This is the 0 differential forms, and in degree 1 it's actually canonically isomorphic to the degree 1 differential forms. So that's very good. And this is kind of one of the standard examples. You can improve on it by tensoring this algebra with itself and using the Kunis formula if you like. But if you take another algebra, which is actually rather innocent, then it completely breaks down. So let's look at this one. Just, well, this is also a nice commutative algebra. And it's an algebra, say, of functions on one point, but infinitesimally thickened. So in algebraic geometry, it will say it corresponds to a zero-dimensional algebra, but maybe with a little extra information. And in this case, you can also write down a projective resolution. More, it's similar to the one above, but well, it's slightly more difficult, so that I didn't want to spell it out entirely. But you can write down this projective resolution, and you can readily compute it. And actually, the outcome is written over there. And surprisingly, in this case, the Hochschild homology in higher degrees is never zero. Although the algebra itself is something like, well, it corresponds to a zero-dimensional geometric object, the Hochschild homology it extends to arbitrarily high degrees. So this certainly doesn't reflect differential forms well. But yeah, well, that's the way it is. This is the functor. The Hochschild homology functor is the one we need because it can be generalized to non-commutative algebras, and more naive differential forms cannot.
But you, just one comment, you can say, I mean, that Hochschild homology tells you that the fact that the Hochschild homology is non-zero in all degrees tells you that the algebra is singular. Right? So if
Excuse me?
That the fact that the Hochschild homology doesn't vanish of this algebra, that doesn't vanish in infinitely many degrees, is telling you that the algebra is singular.
That's right, sure. Yeah,
yeah. So it's a good thing of Hochschild homology that it doesn't vanish, because it tells you that the algebras are singular. I mean,
sure, yeah, it detects the singularity at the origin. That's or it detects that there are nilpotent elements. So certainly it has interesting information. That's true. Okay. Now let's move on. So in general, if you have a commutative algebra, then in fact you can endow this Hochschild homology with the structure of an algebra. There's something called the shuffle product, which is somehow, it's similar to a product of differential forms, but you have to work a bit to make it fit well. And it's not commutative, but it's graded commutative, so the terms commute up to a sign. And then, well, there's this well-known theorem due to Hochschild, Kazhdan, and Rosenberg, saying that if you start with a complex affine variety and then you require that it is non-singular, so then the algebra of functions on this variety is very well behaved. It's what people call a smooth algebra. And then really the Hochschild homology of the algebra of regular functions of this variety is isomorphic in a natural way to the differential forms, to the algebraic differential forms on this affine variety. And in fact, if I'm not mistaken, this is in isomorphism of algebras. So this is really the reason why the Hochschild homology is regarded as non-commutative differential forms. And well, for comparison with later situations, I also wondered, so what happens if you take not just a non-singular affine variety, but you make it into an orbifold by dividing out the action of a finite group? Well, certainly if you take an affine variety and you divide out a finite group, it's again an affine variety. But dividing this out, you may introduce certain, well, say mild singularities, that I call here orbifold singularities. And then, yes, well, the algebra of functions on V modulo G is thus the G invariant functions on V by definition. And if you want to compute the Hochschild homology of that, it's actually not so easy. I mean, it works well in the case that this quotient is really non-singular, so then it's really, then you can apply the Hochschild-Kazhdan-Rosenberg theorem and you get this outcome. But in cases where this quotient is singular, I'm not even sure what comes out. So I tried some examples, and well, one of the first examples where you have a quotient which has a singularity is just you take C2 and you divide out by multiplication by plus or minus 1, and at 0 there's a small singularity. And the algebra is just this. It has 3 generators, but they are related. Well, yeah, this is it's almost like a polynomial algebra in two generators, but still the Hochschild homology seems to be quite different. At least in degree 0, you can already see by hands that there's a non-trivial contribution, because you can just take the wedge product of dx squared with dy squared with dxy, and that in fact presents a non-trivial element in the third Hochschild homology. So there also the Hochschild homology extends beyond the dimension of the underlying variety. So yeah, this Hochschild homology, it behaves in some intricate way if there are singularities in your varieties. Okay, and yes, well, so I wanted to compare this, well, with things involving smooth functions, and then, yeah, if you look at algebra of smooth functions, you automatically get a topology with it. It's typically going to be a Fréchet space and a Fréchet algebra. And then also, well, since we are dealing with Tor functors, we certainly need to look at tensor products. And yeah, just algebraic tensor products are not good enough. You will not end up with Fréchet spaces again. So we use completed topological tensor products here, a so-called projective tensor product, which is the most common choice, in fact. And then, well, then there are further complications of topological nature, namely if you want to have exact sequences of modules over such a Fréchet algebra, then just exactness is not enough. In fact, you want them to be exact in some topological sense, and then the correct requirement is to say that they are split as sequences of Fréchet spaces. So there's a continuous splitting as vector spaces. And then, well, with these notions and such a tensor product, you can define Hochschild homology in a good way also for Fréchet algebras, namely as the Tor functor in the category of Fréchet bimodules, or rather in the category of modules over this A tensor hat A op. So that mimics the previous definition. And then the previous results, well, say in particular about the Hochschild-Constant-Rosenberg theorem, it has a smooth analog, which was discovered by Alain Kohn, I think. This tells you that if you start with an algebra of smooth functions on a manifold, let's say C complex value smooth functions, then the Hochschild homology of that algebra is naturally isomorphic to the differential forms on this manifold. This is a smooth manifold, or a smooth differential forms. And initially, Kohn, I think he proved it only for compact manifold, but later people used somewhat different techniques, and then it was also established for arbitrary smooth manifolds. So that's very good. That's a nice property of this Hochschild homology functor. And here, yeah, well, but remarkably enough, it doesn't pertain to continuous functions. Somehow, well, I mean, it would be natural if you are interested in C-star algebras to apply Hochschild homology to a commutative C-star algebra, so continuous functions on some compact Hausdorff space. But yeah, it produces no interesting results. In degree 0, you get the algebra back, which we knew already. And in higher degree, the Hochschild homology of an algebra of continuous functions is just 0. Somehow it seems to reflect that you cannot really build differential forms by starting with continuous functions. It's not clear what should come out. And in any case, if you plug in the usual complexes which compute Hochschild homology, they are all too trivial in some sense. This algebra of continuous functions is too complete to really do these Tor functions and Hochschild homology in a meaningful way. And this statement about, well, commutative C-star algebras, in fact, also applies to many non-commutative C-star algebras. In general, for a C-star algebra, Hochschild homology is not an interesting invariant.
Just a little question. So, I mean, I know about an analogous result for stable C-star algebras, and I know the reason. But for commutative C-star algebras, I don't think I recall this. Do you have some vague idea of what the argument is?
Oh, damn. No, this is too long ago.
Okay. No,
yeah, I must look it up. This is something which I copied it from my thesis work like 15 years ago.
Oh, I see. So it's something that Kohn proved, or?
well, at that point, I had a reference. So
Okay.
I will look it up later.
Okay, okay, thank you.
Okay, so now let me move on to the algebras that I announced in the title, finite type algebras. And these are algebras, well, which are selected for the purpose that, well, on the one hand, they occur in settings which I find interesting in representation theory. And on the other hand, there are many techniques which can be applied to these algebras which don't work so well for more general algebras. So what is a finite type algebra? Well, finite type refers to the fact that it must be an algebra over something else, and not necessarily over a field, but over a commutative algebra. And this commutative algebra, I take here the regular functions on some affine variety, and it can be any affine variety in this setup. It may be a singular variety. It doesn't bother us too much here. And then you want this algebra to be of finite type, meaning that it has finite rank as a module over this commutative algebra that acts on it. And typically, if the algebra A is unital, then this O of V sits inside it, and then you can say that's a finite rank over this subalgebra. And a general finite type algebra is one which is of finite type over O of V for some well-chosen V. So this is it's a reasonable class of algebras. Another way to see it, at least if the algebra is unital, then you can say you can require that the center is a finitely generated reduced algebra, so then it will be O of V for some V, and that the O has finite rank over its center. So that's one way to think of it. These are algebras which are of finite rank over their center. And in fact, well, these were first defined by Kazhdan, Nistor, Schneider in a paper. And in fact, well, they just allow any finitely generated algebra as the center, and they don't need it to be reduced, in fact. But okay, I will stick to this for this talk. And well, what makes it nice, this class of algebras, is, well, since it is of finite rank over a commutative algebra, it is in some sense not far away from commutative. I mean, of course, it can very well be not commutative, but if you are, well, you can write down higher commutators, say of k elements, and if you take k large enough, then in fact all higher commutators will vanish. So in that sense, it's really close to commutative.
Sorry, question. When you say finite,
I mean, there's a generalization of the notion of a commutator of two elements, which is somehow like we take a commutator of k elements, where k is some natural number. And this is a way to measure how non-commutative an algebra is. And if you take k times k matrices, then somehow the k-fold commutator will vanish. And if you take k plus one size matrices, then the k-fold commutator doesn't necessarily vanish. So, and in this case, you can always find a case such that the k-fold commutator on this algebra vanishes. And well, related to this, if you have an algebra which is of finite rank over its center, then it's easy to see that the dimensions of the irreducible representations are bounded by the rank of this algebra over its center. So certainly there's a uniform bound on all the dimension of all irreducible representations. So the representation theory is in general, is manageable in some sense. And another, well, technical advantage is that if you start with a finitely generated module, then it's easy to produce projective resolutions by free modules of finite rank, because you can reduce it in basically to the case of modules over the center.
Sorry, a little question. In your definition of finite rank, you allow for the torsion of A as an OB module to be as large as you can imagine?
Yes. I think that this is something you should allow, because I also want to allow quotients of such algebras. So, yeah, well, it turns out it doesn't really matter so much. Okay, so let me give you one non-trivial class of examples of cross-product algebras. And I will do this both in an algebraic and in a smooth setting. So, okay, let's take a variety V, which is either a non-singular affine variety over the complex numbers, or it's a smooth manifold, say, over the real numbers. And then you take the algebra of functions on this, so either the regular functions on the affine variety or the smooth functions on the manifold. And well, to make it non-commutative, I involve a finite group which acts on this variety, and then it also acts on the functions on this variety. And then you can build the cross product algebra of this commutative algebra with this, well, say the group algebra of the finite group. So as the vector space, this is just the tensor product, and then the multiplication takes into account how this finite group acts on this commutative algebra. So this is a well-studied class of algebras, and in fact, well, are they of finite type? Yes, surely. Yeah, this business is of finite type over AG, at least in the algebraic case. And well, yeah, the Hochschild homology of these algebras was computed by Brilinski and Nistor in various papers, making it even more detailed. And it turns out that naturally you can identify the Hochschild homology of such a cross product with differential forms, but not just differential forms on V, but you need various sub varieties of V, namely those fixed by the various elements of your group G, and in total you take well, G invariant forms on this direct sum. And the same works if you do it in a smooth setting. This is probably only due to Easter in the smooth setting. I'm not entirely sure. And then you get, of course, smooth differential forms. So this is, in some sense, it generalizes the Hochschild-Rosenberg theorem, but its proof, of course, reduces things to the Hochschild-Rosenberg theorem. And well, if you want, you can say on the right-hand side, this is also differential forms on some variety. And the variety is, well, take the disjoint union of these VGs over all elements in your group and then divide out your group G. So you can write it down in these formulas. You take all pairs V and G and V times G, for which V is fixed by G, and then you divide out the natural action of G, which is given by this formula, just well, the action of V and conjugation on the G factor. So the Hochschild homology of this cross product in either the smooth or the algebraic setting recovers algebraic or recover differential form on this quotient, this well orbifold-like quotient. So this is the one example of a non-commutative finite type algebra that I wanted to bring up. In practice, I've looked at very many examples of such algebras, but okay, these are rather detailed and maybe not so interesting from this general point of view. So I thought, let's stick to this. But I thought I do want to compare this to representation theory, and in particular this final space here on which we take differential forms. Yes, well, so we saw in a few sheets ago, the Hochschild homology in degree 0 tells us something about irreducible representations. And let's analyze the irreducible representations here, because that's not difficult. And there's a general strategy which applies to any commutative unital algebra which has a finite group acting on it. And then in the same way as before, you can build this cross product. So A is, you think of as either the functions on an affine variety or the functions on a manifold, and you build this cross product as before. And then how do you produce irreducible representations? Well, you reduce things to first representations of A, and then you look what happens to your group. So you start with an irreducible representation of A, that's just a character of A, and you look at which elements in the group stabilize this representation. Well, this will be a finite group G sigma. You take an irreducible representation of G sigma, and then this tensor product is a meaningful representation of this cross product where you just have a smaller group here. And it's in fact easily seen to be an irreducible representation. And then the next step is you induce from this smaller algebra to the full cross product algebra. And this turns out to preserve irreducibility under the conditions that I stated there. And in fact, this produces you all irreducible representations of this cross product. This is, well, one of the things discovered by Clifford, or maybe even already Frobenius in this setting. It is very classical. And you can also analyze in these terms when two of these data, sigma and rho, give rise to the same representation. That's only if the pairs sigma rho and on the other end sigma prime rho prime are related by the action of your group in this way. You have your group acts naturally by composition with, well, the conjugation operation by G or the inverse of that. And if these two are in the same orbit for this G action, then they give the same irreducible representation. So in this way, for such a cross product algebra A cross product G, you get an easy parameterization of the irreducible representations with another quotient. Maybe you take the pair sigma rho, where sigma is an irreducible representation of your commutative algebra. So those will typically be parameterized by V if you think of A as functions on V. And another object, which is an irreducible representation of a stabilizer group. And you divide out G, where the action of G is given by this formula. And well, this is the natural way to parameterize the irreducible representations. So let's compare this with the previous sheets. So on the previous sheet, no, I think that's over. Let's do just in one example. So an example of a more geometric nature. So I take a space, just a square, take smooth functions on that, and I take a 4-element group acting on this square by reflections along these two lines written down there. So the point in the middle is fixed. And then, well, so the irreducible representations, if you compare it with the previous sheet, they are parameterized by the quotient of this square by the group, but it's a promoted, an extended quotient, which means that somehow, if you look at it just from a geometric point of view, you actually get some non-Hausdorff points. So the quotient looks something like this. Like most of the time, if you start with a character of this commutative algebra, you get only one irreducible representation lying over it. If you start with a character which is fixed by one of the two reflections, then you get two irreducible representations. And if you start with the character evaluation at 0, then in fact, there are 4 irreducible representations of this algebra with that as central character. So this is the space of irreducible representations is here a non-Hausdorff space, which is not far away from a manifold, but it's definitely non-Hausdorff. On the other hand, you can look at this Brzezinski-Nistor way to compute the Hochschild topology, and there you also had a similar quotient. But there the quotient is you take the square and but you take it, you enhance it by taking the elements of your group with it, and then the elements in your square which are fixed by the elements of your group, and then you divide out the G. And in this case, the space looks similar. You have one big square, which is the contribution from the unit element in your group. You have a line over here, which is a contribution from one reflection, another line contribution from another reflection, and a dot, which is a contribution from the element -1 of this group. So you see that the two quotients here are very similar. And in fact, well, yeah, the space of irreducible representations, if you deform it a little bit, you get this quotient used by Brzezinski-Nistor. So in this case, you can say that the Hochschild homology of this algebra is somehow, it's like differential forms on the space of irreducible representations, but modified a little bit. And this is one way which is reasonable to think of Hochschild homology in more general settings, at least if there are not too many singularities. Of course, in completely general cases, it will fail, but in cases without bad singularities, this is a reasonable way to think of it. In particular, for finite type algebras, where there are not so many singularities, this is a reasonable viewpoint. Okay. So now let's move towards my goal in this talk about comparing algebraic and smooth versions. So one simpler version of this is localization. This can be done purely algebraically. You take a multiplicatively closed set of the center. Well, let's say for instance it's the complement of some ideal. And then you can localize an algebra by adding the inverses of this multiplicatively closed set. And this operation times S inverse is an exact operation. And it's easy to see that this produces you a natural isomorphism between first localizing and then Hochschild homology, or first Hochschild homology and then localizing. That's a standard thing.
Is your ideal prime?
Excuse me?
Is your ideal a prime ideal?
Yeah, it should be a prime ideal, I guess.
Yeah. Otherwise, S is not a multiplicative.
Yeah, sure. Yeah, it must be prime. Yeah, thanks. Okay, and a more difficult operation is completion. Well, with respect to some ideal, again, you can take it prime. That's probably a good idea. Maybe, well, it doesn't matter so much. Well, okay, so you can, there's this operation of taking completion with respect to the powers of an ideal, and you can apply this to any module over a commutative algebra, and this is then get some kind of completed module, and it will be a module over a completed version of the algebra and the commutative algebra itself. And yes, well, this is an operation which, well, I mean, given on a manifold, this really means like you take an ideal, typically ideal functions vanishing at one point, and then this completion is somehow localizing at this point, but it's stronger than that. It's also completing, and it looks at only extremely small infinitesimal neighborhoods of this point. And this is an operation which in fact can be applied to any finite type algebra over OV. And well, you can complete the algebra itself by this formal completion process. And you can complete all modules, and you can also do the same with bimodules if you like. And well, Kazhdan, Nistor, Schneider in their paper on finite type algebras proved in fact that this algebra of formal completion with respect to an ideal, this operation commutes with the operation of Hochschild homology, in the sense that you take Hochschild homology, then you formally complete it in this way. And that's isomorphic to first completing this algebra and then taking the Hochschild homology. Well, there are complications. I mean, you must say precisely what you mean here by Hochschild homology, because in this process, you have introduced an algebra which has additional structure. It has some kind of I-adic topology, or you can say it's a filtered algebra, and you must take that into account when computing Tor groups or defining Hochschild homology.
So you complete the tensor product, right? Yes,
you have to complete the tensor product, yes. And well, one part of it, the most important part of this theorem is in fact that this functor tensoring over OV with a completed version of OV is an exact functor. So that means that the completion is flat over the algebra itself. That's not enough, but that's the most of it in some sense. And yeah, as you just mentioned, in fact, one thing that you must do here is to define this Hochschild homology in terms of Tor functors. You must use the completed version of the tensor product, and one way to do it is like this: you first take the normal tensor product and then you complete it. So let's also check what happens there in a simple example. So the algebra of well, polynomial functions in one variable. Then you take the ideal of functions vanishing at 0, then the completed version is just, of course, the power series centered at this point. And then you can look at this algebra A tensor A op, but then in the completed version, and that's a formal power series, but then in 2 variables. And there you already see that there's a difference between, well, just the algebraic tensor product and the completed tensor product, because the algebraic tensor product here is really smaller than these formal power series in 2 variables. You must think a bit of what is the difference, but it's really smaller. But okay, and this version, formal power series in 2 variables, is in fact the better version. And you can compute Tor groups in that with that idea, with that algebra in the same way as before, basically. So if you compute this Hochschild homology, you must first take a projective resolution into the modules over this algebra. And we take the same projective resolution as we had in the purely algebraic case, and it works. It's still a projective resolution here. And then you compute the Hochschild homology in the same way, just by the process of tensoring this projective resolution with the module another time, and then you get this complex with 0 differentials. And you see that you get again some kind of differential forms. In degree 0, you get the algebra back, and in degree 1, you get some kind of differential forms on this formally completed algebra. So this will be a very local version of the result I'm going to tell you in a few minutes. Okay, so now let's really move on to topological algebras, but then those which are of finite type. So this hasn't been defined yet. So let me define it here, what I want to do. So basically what I want to do is to have Fréchet algebras which are of finite rank over the smooth functions on some manifolds, and usually these smooth functions will then be embedded, but that's maybe not necessary. You can also say it has to be a module over smooth functions on some manifold. But it turned out that for the applications that I had in mind, that was not general enough. I actually needed smooth functions on an orbifold. So it turns out that maybe a more interesting class to look at is that finite algebras, which are Frege and of finite type over the smooth functions on an orbifold M modulo G. And then, well, G is just a finite group. I mean, maybe you can develop it also for infinite groups, but here I stick to finite groups. So typical examples there are, well, of course, the smooth functions on a manifold itself. This is a finite type algebra over itself, but it's also a finite type algebra over the functions on M modulo G, at least if G is and if M is compact. And also this cross product is also a finite type algebra. In this case, it's not a finite type algebra over C infinity of M, because it's not C infinity of M doesn't live in the center, but it is a finite type algebra over the G invariant functions in C infinity of M. And again, the compactness of M and the finiteness of G well, imply that these two algebras are finitely generated over C infinity M and the G invariance there. So that's one source of examples. Another source of example is, okay, you take the previous notion of a finite type algebra in a purely algebraic sense, and then you assume that your affine variety is non-singular, and you regard it as a smooth manifold, and you tensor it up with smooth functions, then you get again another finite type algebra of topological kind. And in fact, if you look into representation theory, where I come from, then in representation theory of real reductive groups and in the representation theory of reductive p-adic groups, there are examples of algebras of this kind which have relevance for certain representations. And let me also mention that, well, this kind of algebras of smooth functions on an orbifold, this orbifold, if it's not a manifold, then in fact, this algebra is already slightly too tricky to compute its Hochschild homology. And I do not know what it is, in fact, in general, if M modulo G is not a manifold. But okay, I do not really need that. We will see later. So, okay, so we have this kind of algebras, and then, well, to compare it with, well, to compare, say, the Hochschild homology of some underlying algebraic version of a finite type algebra with such as a topological version, we will apply some well, tensoring with smooth functions. And like in the case of formal completions, we need a flatness result. And this is in some sense the main technical point of the paper of David Kazhdan and me, that we proved such a flatness result. And it needs some input. It doesn't work in full generality. You need, well, I start with a complex affine variety because that's the entire setup. And then inside there, I want to have a smooth manifold lying inside it. But you need some conditions. So it needs to be analytic for certain very technical reasons. And you also want it to be Zariski dense, because if it's not Zariski dense, then you rather replace V by the Zariski closure of M. And the most important condition is, in fact, that the tangent spaces behave like this. So the tangent space of V at the point M is, in fact, it's a complex vector space because V is a complex variety. And the tangent space of M at the point M is a real vector space because M is just a real smooth manifold. And then if you tensor it up with the complex numbers over the reals, they should be equal. So this means something like the dimension of V as a complex variety is equal to the dimension of M as a real manifold. And to get more generality, I also want to allow for an action of a finite group which reserves both the structures of the affine variety and of the smooth manifold.
So sorry, so you allow singularities in V, right?
Yes, but I do not allow those singularities may not lie on M. So M is smooth as a manifold. So the singularities that are in V will disappear if you restrict to M. So, and under these conditions, you can actually prove that this module of smooth functions on M, or say G invariant smooth functions on M, is flat as a module over the regular functions on V, which are G invariant. So otherwise the functor tensoring with smooth functions over regular functions, both G invariant here, is an exact functor. And yeah, this is kind of surprising statement because you're really mixing two worlds, one of algebraic functions and one of smooth functions. Well, it's actually necessary to say precisely. Well, now this is the purely algebraic tensor product because on the algebraic level there was nothing else. So yeah, and it's also just the exactness is also measured purely algebraically. Although we might want, in fact, to be the result to consist of Friché spaces, this is maybe not necessary. The exactness doesn't tell you that. In fact, in many cases of this paper, it is necessary to prove that certain modules are Friché, and this usually comes from the fact that you consider, say, finitely generated modules. That is a condition which is sufficient to get Friché modules out of this exact functor. And well, I looked for this, but it seems, well, okay, if you forget about this group G, then, well, firstly, it becomes easier, although not much easier, but it becomes a little easier. And secondly, well, it seems to be unknown before. I mean, it was known in the case where M is equal to V. Well, of course, then this condition doesn't hold anymore, but if G is 1, if G is trivial and M is equal to V, then this is a relaxation which is allowed. That case was known. I found some hints on that on the internet, but I couldn't find a clear-cut statement in the paper. But in general, even, yeah, well, it seemed to be unknown. And yeah, the proof is kind of technical. I mean, it proceeds via comparing certain tensor modules by formally completing them at various points and then comparing them at each point separately. But it involves some technical intricacy by really explicit and estimates in terms of smooth functions. So I will not make that explicit here. So yes, so now let's apply this to Hochschild homology. So I know that this functor of tensoring with smooth functions over regular functions is an exact functor, and that then you can apply it to finite type algebras. You need at some point to use that you have finite type or you need projective resolutions of finite ring, and then you quickly get this kind of result that the functor of tensoring with smooth functions over regular functions commutes with the functor of Hochschild homology, where, well, in the topological sense, we need to take the topology into account, to take topological tensor products and also well, split exact sequences which are split as sequences of Friché spaces. But then it really works out nicely, and you get this nice comparison result. So just to illustrate, let us do this for the case of these cross product algebras. So let's say I take the cross product algebra, I take V to be some variety on which Gx, I take this cross product. Then on the right hand side, well, if you take this expression here, then if M is compact, then it's not difficult to see that this expression here contains all smooth functions on M, and you get easily the cross product of the smooth functions on M with G. And this is something which was computed by Bielinski-Nistor. And now we have an alternative computation by first doing it on an algebraic level and then tensoring up by smooth functions. And well, of course, it's not hard to see by hand that these two things give you the same, but okay, it's a nice example which can then, by this theorem, be generalized to algebras where, in fact, it may be difficult to compute either of the two sides. Yes, well, so this theorem, this comparison theorem for topological and algebraic Hochschild homology, so it relies in some sense on what you could do with formal completions, but you can also say it's somehow a globalized version of this formal completion result that was obtained by Kazhdan, Nistor, and Schneider. And as I said, the crucial part is that this algebra of smooth G invariant functions is flat over the algebra of regular functions on some underlying variety. And yeah, well, I have here, I've just posted you one example. Well, how I arrived at this question was really by questioning representation theory concerning the Schwarz algebra associated to a reductive periodic group, where I wanted to compute the Hochschild homology, and the techniques developed to prove the theorem actually were also the technique used to compute the Hochschild homology in that particular example. So I really had some application, not literally of this theorem, but of the techniques used for this theorem. So finally, let me go back to where I started, comparing algebraic and differential forms. So here I restate the theorem, well, which needed a few more conditions. But okay, now let's look at the case where you plug in a commutative algebra, say functions on a manifold. Well, okay, I repeat the conditions for the theorem. Phi is an affine variety, M is a manifold, which is strictly dense, it has to be analytic. And you have this condition on the tangent spaces at any point. And then, well, one question you may ask is, okay, suppose you take n forms on V, you tensor them up with smooth functions on M, tensor them over a regular function. Do you actually get all smooth differential forms on this manifold M? And well, it's easy to see that the right-hand side here embeds in omega n of M, but that it's actually surjective, I wasn't sure. I proved this in the case that if you assume that M is either a compact manifold or M is really a real algebraic variety. And in general, well, I don't know. It may be false actually in some nasty examples. But okay, let's assume that we are in one of the cases where this isomorphism holds. Well, then you can apply the previous results to this algebra O of V. You forget about the group G, and then you recover from this theorem. Well, on the right-hand side, you get O of V tensored over O of V with C infinity M. That's just C infinity M. So you get HHN of C infinity M. And on the left-hand side, you get exactly this expression here. So then you get the n forms on your smooth manifold M. So then you can get, well, again, an isomorphism between n forms on the smooth manifold and Hochschild homology of the smooth functions on the manifold. So then we recover what we knew already long ago, of course. And this is the, well, yeah, it is just an argument or a corollary of this result, which well, it's satisfactory in the sense that we know it's true and it confirms what you already knew. And it indicates that this is maybe a nice generalization of a well-known result about Hochschild homology for commutative algebras to Hochschild homology for, well, non-commutative algebras, which are still not so far away from commutative algebras in the sense that they are of finite rank over commutative algebra. So here I have completed the circle of ideas which I wanted to present you for comparison of algebraic objects and smooth objects. And well, this also completes my talk. So I thank you for your attention, and any further questions are welcome, of course.
Okay, thank you very much, Maarten. Are there any questions from the public? Let's see. I have a general question. So, have you looked at what happens with noncommutative theorem? I mean, say the image of the S operator in cyclic homology. So, for example, in the case of the orbifolds that you discussed previously, that you get homogeneous singularities with respect to some weights, that would be an easy case. Then the algebra is graded, and you essentially, I think, the S operator is 0, and then everything trivializes. So this in this case, perhaps, I mean, the comparison between the non-commutative.
You mean you want to actually use this theorem then to compute some things in this algebra with singularities?
Yeah, so I mean, the RAM, so you can ask non-commutative, the RAM, right, is defined, it's a byproduct of cyclic homology, the image of the periodicity operator. I can also define by taking non-commutative differential forms, modding out by commutators, graded commutators, and taking the homology. So this makes sense for both plain algebras and algebras with a topology. And perhaps, at least in some cases, one would try and use, if not your results, maybe your methods, or a combination of the two, to try and see whether one can also compare the relation between purely algebraic RAM and
it's maybe possible, in fact. Yeah, I didn't think of that. Yeah, for that you really want to use this flatness result, which I showed. Yeah, but maybe it's not enough.
Yeah, I mean,
this is a good point. Yeah.
Of course, you do not expect this to be modules over the algebras of functions. So it's not.
No, this is the problem. Yeah.
Yeah, but maybe I don't know. Maybe they should be the same as the same C vector spaces in the case when the homologies are finite.
Yeah, this is a very good question. I must admit I had not considered this, so I can't really say what comes out, but I will investigate it.
Okay, and I think in the purely commutative setting, there is some theorem of Grothendieck that says that if you take the purely algebraic, the rank homology of the affine algebraic variety and that of the analytic and the RAM and homology of the analytic variety, you get the same thing. So
yeah, that's right, but that's in fact a more elementary result.
Yeah.
And that's something that you could formulate in terms of the periodic cyclic homology. And I actually worked on that, but that's already very long ago. It's much more elementary to prove such a result in a non-commutative setting than these theorems, which I presented here.
In a non-commutative setting or in a commutative setting?
Oh,
on both.
You can prove it for the non-commutative algebras also of this kind. That's something. Well, it's actually something about which I wrote the paper some 15 years ago.
Oh, I see.
If you have an algebra, a situation similar like what you sketched with what Grothendieck did, on the one hand you have, say, regular functions on a variety, on the other hand today smooth functions on the same variety, and then you ask for the RAM cohomology in either the algebraic sense or the smooth sense, and they are isomorphic, and this you can reformulate as saying that two algebras have the same periodic cyclic homology, and if you have reformulated it in this way, you can generalize it to finite type algebras, in fact.
So here, there's a question from the audience. Devarshi asks, is it plausible that the bimodule connection on OB extends to one on C infinity of M?
This I don't know. Sorry, I'm not sufficiently familiar with that, I'm afraid. And, I don't know. Sorry.
Yeah, maybe in the I mean, the connection on omega n, the non-commutative differential form, is what gives the triviality of the Hochschild complex in higher degrees. So if you have a connection on omega n, omega n, that means omega n is a projected bimodule, and so the resolution, the bar resolution stops there. I mean, you can continue, but you if you chop it there, you still get the resolution. The projected.
I see. Okay, in the sense that you have an algebra of this given dimension n. Yes, or
Yeah.
of manifold given
Yeah,
dimension,
and
yes.
the fact that you could extend it to infinity would mean that from that the same certificate for finite dimensionality that you have on the algebraic side extends to the infinity setting.
Yeah, oh, this sounds reasonable that you can, in fact, if you have done it on an algebraic setting, that you can promote it to a smooth setting just by this tensoring operation. I was not aware of such a use, I must say. So this is again a very interesting suggestion, which I will study. Yeah. Write this down so that
Okay. So I don't see any more questions. So I will thank you for wonderful talk, and I will stop the recording.
Okay.